Welcome to the Explainer. Today, we're diving into a genuinely fascinating mathematical puzzle that sits right at the very heart of human behavior and strategy. For decades, game theory has basically been obsessed with just one single question. What happens when one person decides to cheat the system? But let's be real. In the actual world, people don't just act in a vacuum, right? They form alliances, they scheme, they coordinate. So how do we mathematically predict outcomes when people decide to team up instead of acting alone? Well, that's exactly what we're going to unravel today by walking through a seriously groundbreaking new paper on computing equilibrium. So here's our roadmap for today. We'll start with when Nash equilibrium fails, then introduce the MASC solution. After that, we'll map things out with the utility dependency graph, pit the correlator against the deviator, and finally weigh exploitability versus social welfare. Let's get right into it. All right, kicking things off with section 1, when Nash equilibrium fails. Think about the classic prisoner's dilemma for a second. You've got two accomplices interrogated in completely separate rooms. The classic math assumes they make their choices totally isolated from each other. But what happens if they can coordinate? What happens when players decide to literally team up? Well, suddenly those single-player mathematical rules break down entirely, because what's best for the individual in isolation is definitely not what happens when a group pools its resources together.
And that brings us to arguably the most famous concept in game theory, the Nash equilibrium. Now, don't get me wrong, it's a brilliant concept, but it has one massive, glaring limitation. It guarantees only that no single player can improve their utility by deviating unilaterally. It completely and totally fails to protect against profitable, coordinated deviations by multiple people acting together. Basically, the second a coalition forms, Nash equilibrium just completely collapses.
Let's actually visualize this. Look at this nested diagram mapping out all the attempts to fix this exact problem over the years. We've got these different layers of strong equilibrium notions. The outermost layer is the coalition-proof equilibrium. Then as we move inward, we hit strong, then strictly strong, and finally we land right at that dark blue center, which strictly requires zero total gain for any coalition whatsoever. But here's the catch. These inner layers, they represent mathematically impossible standards. Demanding that no group can ever, under any circumstances, find a profitable deviation sounds amazing in theory. But as the research proves, these perfect equilibria basically never exist in real complex games. We've literally been chasing mathematical ghosts.
Which brings us nicely to section 2, the MACE solution.
So if perfect immunity to coalitions doesn't exist, what on earth do we do? Look at this direct comparison. The old way was demanding absolutely zero coalitional gain, and like we just saw, that's practically impossible. But the new way, the MACE way, which stands for Minimum Average Strong Equilibrium, completely shifts the focus. Instead of demanding absolute perfection, it just minimizes the maximum average gain that any deviating group can achieve. It basically asks, how can we make cheating together as unappealing as humanly possible? I think this quote perfectly sums up the entire shift in thinking. We aim to compute the most stable strategy profile, even if a perfectly stable one does not exist. It's so pragmatic, right? This approach actually guarantees an outcome. By shifting away from this rigid pass or fail requirement into an optimization problem, we finally get a reliable mathematical foundation that we can actually build on. Moving right along to section 3, the utility dependency graph. Now, actually computing this new MACE standard is incredibly complex. To tackle it, check out the utility dependency graph on the left side here. You see nodes 1 through 5 representing our players, and they're connected by lines if their actions affect each other. Honestly, it looks like a tangled web. But look over at the right side. This is the tree decomposition. The algorithm takes that messy web and elegantly breaks it down into small overlapping subgroups, which we call bags. Notice how players 1, 3, and 4 form that top bag, and then it branches out from there? This is a real game changer, because it allows the math to break down massive, overwhelmingly complex social interactions into small, localized problems. We can optimize those independently, and then link the whole shebang back together. And this structure introduces an absolutely vital concept, tree width. It's a formal measure of how sparse and, well, tree-like a graph is. You see, calculating a MACE is an NP-hard problem, which is basically mathematician speak for, please, whatever you do, do not make me run this on my laptop. It is computationally brutal. But the researchers prove something incredible here. The calculation time doesn't scale based on the total number of players.
Instead, it scales exponentially based specifically on this tree width barrier. So if your social web can be broken into neat little tree branches, you can solve it efficiently, literally no matter how many total players there are.
Let's transition over to Section 4, the correlator versus deviator. Let's look at the actual mechanics of how this MACE is calculated. It builds this completely fascinating cat and mouse metagame. We're literally pitting two algorithms against each other. Step 1. The correlator tries to pick a system-wide strategy that keeps order and minimizes any group's gain. Step 2. The deviator hunts for the ultimate loophole. It's actively trying to find the exact coalition that maximizes a payout against the correlator's rules. And Step 3. They iterate. They learn from each other using an algorithm called Follow the Perturbed Leader, or FTPL. It is a straight-up virtual arms race that ultimately converges on our optimal MACE strategy. To see why this specific cat and mouse calculation is so vital, let's look at these charts measuring coalition exploitability. Basically, how vulnerable is a system to groups teaming up and breaking it? The left graph tracks the number of players on the bottom axis, and the right graph tracks action size. See that purple line with the cross markers? That is MACE, and it stays incredibly low and stable across the board. Now look at the yellow and red lines. Those represent classical learning algorithms like FTRL and Hedge. As the games get larger and more complex, their exploitability wildly increases. These charts definitively prove that the old algorithms become unbelievably fragile when scaled up, while MASC absolutely holds the line. And we see this exact same terrifying vulnerability confirmed again right here in random polymatrix games. Look specifically at the rightmost chart tracking expected interactions per player. As a network gets denser, as people interact with more people, those classical baseline models curve sharply upwards. The more expected interactions you have, the higher the risk of devastating multilateral deviations. Meanwhile, look at that purple MASE line. It remains steadfastly anchored right near the bottom. The takeaway is clear. If you rely on old baselines in a highly connected world, your system is just sitting there waiting to be exploited.
Okay, bringing it all home with Section 5, exploitability versus social welfare.
Let's translate this abstract math into a real-world takeaway. Look closely at these prisoner's dilemma metrics, broken down into 3 specific subplots. The first subplot on the left shows unilateral exploitability. Everyone basically converges to a low level here. The middle chart shows coalition exploitability. And again, the baseline skyrocket while MSE, the purple line, drops. But the real kicker is the third chart on the right, social welfare. This is the total good achieved for everyone. The baseline algorithms completely flatline at a dismal social welfare of just 0.4. They literally doom the players. But look at the purple MSC line. It shoots straight to the top, actively promoting cooperation and achieving a perfect social welfare of 1.0. We see a similar, honestly incredible result in the stag hunt scenario. Again, 3 subplots. If you look at the far right social welfare chart, there are 2 distinct equilibrium lines you can land on. The old baseline algorithms just get stuck in the lower equilibrium, hovering around a welfare of 0.9. But we can visually see how the purple MASE line successfully climbs all the way up and converges to the absolutely superior equilibrium at the top, perfectly aligning with a social welfare of 2.0. So MASE doesn't just protect against cheating, it actively finds the better world for everyone involved. And this revelation leads us to a powerful new concept, the Exploitability-Welfare Frontier, or EWF for short. Mathematically, it's defined as the maximum attainable social welfare subject to a given exploitability limit. But really, just think of it as a sliding scale. It's the mathematical trade-off curve between accepting just a tiny bit of system vulnerability, meaning letting individuals potentially gain a little bit by cheating, in exchange for a massive system-wide increase in the greater good. Plotting exploitability on the bottom axis against social welfare on the vertical axis reveals this exact trade-off across 4 canonical games. Focus on that solid blue line for the prisoner's dilemma. At 0 exploitability, all the way on the far left, social welfare is stuck at a terrible 0.4. But look at how steep that curve is. By merely allowing the exploitability to slide just slightly over to 0.1, the social welfare rockets straight up to 1.0. This chart pinpoints the exact specific moment where letting go of absolute paranoid individual safety unlocks absolute peak social welfare. And we can actually see the inverse of this concept plotted right here. The bottom axis tracks the weight on individual rationality, which is essentially just how heavily we prioritize pure individual selfishness. In the left chart for the prisoner's dilemma, notice the red line representing social welfare. As we slide to the right, putting more and more weight on individual rationality, the red line drastically drops from roughly 1.3 all the way down to 0.4. This chart perfectly, mathematically, maps the tragic cost of selfishness. Demanding total individual rationality absolutely craters the well-being of the whole group. Which brings us to the ultimate question leaving this explainer. We've seen the mathematical proof, right? Designing systems that demand perfect, airtight security against any individual deviation actually traps us in outcomes with terrible social welfare. MAPSE proves that a tiny bit of vulnerability is the mathematical key to vast cooperation. So when looking at our real-life social structures, our economic markets, and our government regulations, how much risk should society tolerate to maximize the greater good? Thanks for joining me today. Keep questioning the baseline.